Hi guys, welcome to this last video in the series on arterial pressure regulation and the reflexes. In this video we'll cover what might be termed the quote other reflexes. So the first one I'm going to show you is the response to a change in blood volume. You'll recall in the very first video that I did for this lesson, I talked about the two types of receptors we were going to talk about the most were the baroreceptors and the volume receptors. This has to do with the volume receptors, which are in your atria, okay? And so what you see here is an EKG, and what you see is the changes in atrial pressure as your heart goes through the cardiac cycle. So the first thing you'll notice is this hump, which indicates atrial contraction, and you get, following that P wave, which is electrical and propagates fairly fast through the atria, you get a contraction of the atria in response to that, and you get an increase in atrial pressure. And in response to that increased pressure, you get a firing of the type A volume receptors, which you see here, and they send inputs to your brain. So these impulses go to your brain. The more impulses your brain sees, the bigger the increase in pressure here and the higher the atrial volume was, okay, when that contraction took place. Then you see our QRS here. That means our ventricles are getting ready to contract. And our ventricles contract, and our AV valves, our mitral valve on the left, our tricuspid on the right, close. And when those valves close, blood doesn't stop flowing. It keeps flowing, and it accumulates up against that valve, and it actually blows up your atrium. And what you see in response to that increased atrial volume, which takes place because the blood is flowing and accumulating against that valve, is a stretch of the walls. And in response to that stretch, you get firing in your type B atrial volume receptors. These fire in response to stretch of the atrial walls. And once again, the more firing you get, the more volume accumulates. That means that you've got more volume in your cardiovascular system, more volume in the atrium during this phase. Okay? So these two are your atrial volume receptors. And the more blood volume you have, the higher the frequency of impulses. And you see that here. So higher blood volume, a bigger increase in blood volume gives you a bigger increase in the frequency of action potentials and pulses through the nerves from the receptors into your medulla, okay? Your cardiovascular regulatory centers. All right? So here's how this sort of works if we consider hemorrhage, which would be a decrease in blood volume. So we get a decreased blood volume, okay, in response to hemorrhage, in response to decreased volume, right? And that causes a decrease in firing in our volume receptors, okay? And that decreased firing in the volume receptors leads to a increase in antidiuretic hormone, which is secreted from the posterior pituitary, okay? And that, in a nutshell, increases the water retention for the body. It tells your kidneys, hey, don't urinate as much. We need that water to increase blood volume, okay? And so antidiuretic hormone, a diuretic means I urinate more. Antidiuretic means urinate less. Accumulate water within the tissues, okay? And so that increases water retention, and that increases blood volume, okay? So here we have water, increased ADH, and that tells your kidneys, increase the water reabsorption back into the body, and that will increase blood volume. Now, in response to that baroreflex, you also get a drop in mean arterial blood pressure, right? You know that. You've lost blood. We just did it as a Serksen problem. And you know that your baroreflex kicks in as a result of that, and that means that you increase sympathetic outflow through your baroreflex. And that increased sympathetic tone to your kidneys activates the renin-angiotensin-aldosterone system. In this case, you know, in this system you get conversion of angiotensinogen to angiotensin 1, and renin is the enzyme that is responsible for that conversion, and then from there it's converted to angiotensin II, which acts on your adrenal cortex to increase aldosterone secretion, and aldosterone increases in your plasma. We'll talk a lot more about this when we get to the kidney, but for now, all you need to know is increased aldosterone means increased sodium reabsorption, which means increased water reabsorption, okay? And once again, you get an increased blood volume through water reabsorption, in this case through increased aldosterone, okay? So both of those kick in response to a change in blood volume, and both result in an increase in blood volume back toward normal. Now your baroreflex takes place in seconds and minutes, right? Your kidneys, on the other hand, the regulation of blood volume, that takes hours and days, okay? So this is a fairly slow mechanism. This is fairly quick. But the effects of water reabsorption and the increase in blood volume, that takes place over a longer period of time. But nevertheless, this is a reflex that's initiated, and these volume receptors participate, as well as the baroreceptors, okay? Finally, we have a list of other reflexes that are not as important, at least for now. We have the brain bridge reflex. This is probably not important in man. If you increase the atrial volume, you get an increased heart rate, okay? This might make sense to you if you think about it in terms of congestive heart failure, where cardiac output drops, central venous pressure rises, and where the increased atrial volume tells the body, hey, increase the heart rate and get that cardiac output back up. The magnitude of the response depends upon really how strong the baroreflex is, and man, this is way strong, and this is not so strong. So you don't really have to worry about it a whole lot, all right? Not particularly important in man. But something you might want to be familiar with, if it may pop up, you may see it, you know. The chemoreceptor reflex, probably more important in the respiratory system. We'll talk more about it in vital gases. But stimulus is decreased arterial oxygen, and in the case of peripheral chemoreceptors, increased carbon dioxide in the blood in the case of the central chemoreceptors, and decreased pH is picked up by peripheral chemoreceptors as well. The primary response is respiratory, while the decreased pH, if we're talking about the respiratory system, is picked up in the central chemoreceptors. But there are receptors for pH in the peripheral chemoreceptors as well. So something to bear in mind, pH is detected in both. In the case of the respiratory response, you get an increased rate and depth of breathing, okay, and that should make sense to you. Bring in more oxygen, blow off more CO2. There is a secondary cardiovascular response. It is a reflex vasoconstriction and an increased heart rate. This is meant to increase cardiac output and mean arterial pressure, okay, presumably to increase the perfusion of the tissues when there isn't that much oxygen around for them to pick up oxygen from. So when severe hypoxia is present, the cardiovascular response assists in delivery of oxygen to the tissues, okay? Particularly the brain and heart, where, of course, you want to aid that delivery, you know, in preference to other areas of the body, okay? But that's secondary to the respiratory response, which is really the primary response. And we'll talk a lot more about this in vital gases. The CNS ischemic response, or the Cushing reflex, this is a reflex that is initiated in response to either a really, really big change in mean arterial pressure or increased intracranial pressure, okay? So if the MAP drops below 50, this would be like a last-ditch effort to get as much oxygen to your brain as possible in the face of that. The same thing with the increased intracranial pressure. if that's picked up, then your body knows that you better increase perfusion somehow to your brain. And so this would be a response which would be meant to increase arterial pressure and overcome the effect of this increased intracranial pressure so that you can continue to get adequate perfusion. Okay? So either way, this is an extreme response, a big increase in sympathetic outflow, which leads to an increased total peripheral resistance, not in the brain, of course, and a big increase in mean arterial pressure. Okay, that's sort of the idea. And that leads to a reflex bradycardia. If you're talking about a big increase in the mean arterial pressure, you get some bradycardia in response to that. But nevertheless, the mean arterial pressure remains higher overall. And that's definitely needed if you're starting with a big drop in mean arterial pressure, or if you're trying to increase the effect of, let's say, an intracranial mass, where you've got a lot of resistance to flow to overcome. You're going to want to increase your arterial pressure a lot. And you're going to want to make that, in the case of the severe problem, the primary thing, because your brain is paramount. Perfusion to your brain is important to your body above all, and your body knows that. Okay? So this is a last-ditch effort to ensure that that happens. Okay? That's all I've got for this video and this lesson. Thank you for your attention, and I will see you guys in the rooms.